Hi everybody, Physics Ninja here. Tonight what we're going to do is look at the reflection and transmission of a harmonic wave traveling from one string to another string. I want to look at more specifically what are the boundary conditions here where the string is connected, and how do I use that information at the boundary condition to derive expressions for the reflection and transmission coefficients for transverse waves. And the last part we're going to do is look at four limiting cases to make sure it makes sense in our equations and build some intuition on what happens to waves when you go from one medium to another medium. Alright, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. Alright, let's get started. Alright, so we want to look at the reflection and transmission of transverse waves. And what I'm going to do now is consider a long string. On the left-hand side, we're going to call this medium 1. It's characterized with a linear mass density. Right? This is the mass density. It's how much mass you have per unit length for rope number 1 over here. You can write that as dm1 over dx1. Okay. On the other side, it could be a little thicker, could be a little thinner. It depends on what the rope is made of. So it could have a different linear mass density. For right now, we're just going to say there's a different tension. I'll talk about tension in a minute and how they're related to each other, but let's just deal with the tension on the blue string as T1, tension on the green string as T2. Now you can see right away that T1 has to be equal to T2 because guess what? If it's not equal to each other, at least in this case over here, what you're going to have is you're going to have the whole string moving either to the left or to the right because there's going to be a net force, for example, right on the particle at the interface over here. I'm setting the interface here, which is kind of arbitrary. I'm setting it at position x equals to 0. Okay. Now, if we look at the speed of the wave in each medium, the speed of the wave I looked at in a previous video, it's given by the square root of the tension over the line density. Okay, so that could be different because, again, there could be thin or thick ropes connected to each other. Now let's think about the frequency and the wavelength of these waves. So if I look at medium 1, if I shake my hand up and down here to make this string vibrate, what I'm going to have, I'm going to generate a frequency omega 1. Okay, that frequency is going to be the same as the frequency of the green string. So the frequencies have to be the same because it's determined by the source, whatever is creating that oscillation. Okay, so determined by the source. That's very, very important. Now, for both cases, we still have our wave speed equation, which says that the wavelength, the speed is given by the wavelength times the frequency. We just said that the angular frequency is the same, so that means that the frequency of oscillation has to be the same. Well, guess what? If the speed is different, it means that the wavelength is going to be different. Okay, so on side 1, I can write V as having a subscript 1 with a different wavelength, and on side 2, it could have a different speed because of the tension and the line density. And that would mean it would have a different wavelength because the frequency is the same. All right, one last thing now is the wave number. If the wavelength is different, remember we have this property called the wave number. The wave number is simply 2 pi divided by lambda. So again, that could also be a different property for each side of this string on the blue versus the green. All right, so let's go now on the next page. What we're going to do is we're going to generate a harmonic wave on the blue side, and we're going to see how it's connected to the wave that gets generated on the green side. All right, what you could do is just grab the end over here and start shaking it up and down to produce a wave. I'm going to produce a wave, and that wave is eventually going to reach this interface here. Let me go ahead and draw that interface. That's at position x equals to 0. Now the wave that I generated here propagates to the right, all right? And it's going to have a speed 1. It has a wave number k1, and it has a frequency or an angular frequency omega. Now I can write the equation for that as being the displacement, the vertical displacement of that. I'm going to put a subscript I here. This will mean incident wave. Now it's going to be a function of position and time, and in this problem here I'm going to generate a harmonic wave. So it's going to have an amplitude, tells me how high the maximum displacement is, multiplied by cos, and again I could use sine here, doesn't matter. Omega t, actually, sorry, let me just write it a little bit differently here. K1x minus omega t. Now this is a wave that propagates to the right as I shown here. Now once it hits the green area, guess what? Well, some of that energy now is going to get transmitted in the second medium. Okay, and the transmitted wave is also going to propagate to the right. It's going to have a speed v2. It's going to be characterized with a wavelength or a wave number k2. And guess what? It's going to have the same angular frequency. Now this transmitted wave, I can call it y sub t. Again, it's a property of position and time. And now it's going to have a different amplitude. It might not have the same amplitude as my incident wave. For example, if it's a thicker rope, the amplitude might be less, but we'll see. This is the goal of this problem here. I'm going to call the amplitude c and then multiplied by cos. Now we're in medium 2, so the wave number is different, k2x, and now minus omega t, the same angular frequency. Now there's one additional wave that I have to have. Part of this wave might get reflected. The reflected wave, I'm just going to represent it here by this red line. Right, once it hits a medium, part of that energy and part of that wave gets reflected. Okay, the reflected now is traveling in medium 1. So it has a speed v1, it has a wave number k1, and it has the same angular frequency. Now the reflected wave, I'll call it y subscript r, again is a function of position and time. It might have a different amplitude from the incident and the transmitted wave. So I'm going to call that b cosine. Now it has to travel to the left-hand side. So how do I make a wave travel to the left-hand side? What you have to do, if you looked at one of my previous videos, is if you switch the sign here to a positive sign, this is a wave that travels to the left. All right, and the same omega t that applies. Now, one very important thing now is the displacement. So if I'm looking in medium 1 over here, the total displacement in medium 1, guess what? It's going to be the sum of both of those. Right? There's two waves that are superposition in medium 1. So actually what you could do here, let me go ahead and write everything down. So the total wave on medium 1 is just the sum of both of those. So you'd simply write a cos of k1x minus omega t plus b cosine of k1x minus omega t. No, plus omega t rather in this case. In medium 2, what we have is there's only one wave. There's only one wave that gets transmitted. So in medium 2, this is the total wave transmitted in medium 2. So let's just write it as kx minus omega t. And again, don't forget the 2 over here because I'm in medium 2. All right, now the goal is to determine kind of what are these amplitudes of the waves, right? How do we determine these amplitudes given this situation here? So let's go on the next page, and what we have to look at now are boundary conditions. And what are the boundary conditions that we apply right here at the connection between the blue and the green string? All right, so the first thing we have to look at are boundary conditions now, and that's going to allow us to determine these amplitudes, at least the ratio of the amplitudes. All right, so let me just write that down. So what are the boundary conditions that you apply? And the boundary conditions basically are what is going on right here. Okay? If you write your total amplitude here as being the sum of two waves, an incident and a reflected, and in this case for medium 2 as simply being this wave, one boundary condition is that the wave or that the string is continuous, right? The string doesn't break in half once it gets over here, right? So that'll be our first boundary condition, that the string is continuous. Well, guess what? If it's continuous, it means that the displacement, the total displacement on side 1 at position 0 and for every single time has to be equal to the displacement in medium 2 at position 0 and for every single time, right? Because remember, our boundary here is at x equals to 0. So this is a requirement. So all you do now is you substitute x equals to 0 in my total incident wave over here, or the total wave on medium 1, and you substitute x equals to 0 for the transmitted wave. Guess what you get now? That simplifies our expression a lot. So if you do that, you get a cosine. Now, if you substitute x equals to 0, forget about that term. Here you get minus omega t plus b cosine of plus omega t. And here this has to be equal to c times cosine, again, of minus omega t. Now, cosine is an even function, so guess what? It means that whether you have cos of minus something or cos of plus something, it has to be equal to the same, right? You don't have to worry about whether the argument is negative or not. Now you can see there's a big simplification that happens when you do that because you have cos omega t for all the terms. And now we're left with this first boundary condition says that these amplitudes are simply related using this equation. A plus B, so the amplitude of the incident wave plus the reflected wave must be equal to the amplitude of the transmitted wave. So we have one equation now, and we have three unknowns. So guess what? We're going to need at least one other equation if we're going to try to find at least ratios between these different quantities. So we need one more boundary condition. All right, our second boundary condition is, let's call it, II here. II says that at the boundary right here, we also require that the slope is continuous. So the way we write that is that we want the slope of the wave on side 1 evaluated at this position at x equals to 0 has to be equal to the slope at side 2. And again, evaluated at x equals to 0. Okay. Now let's think about what if this is not true, right? Imagine you're a particle here right at the midpoint. And the slope would be different. The slope is telling you the direction of the string, right? So imagine on side 2 you have a tension that's going like this, right? The rope right there at that interface is going down. And imagine that the slope is different. So on this side here, it may be going straight like this. Right? First of all, again, the tension is just simply directed along that string. And what you would have here would be, you would have a net force acting, for example, in this horizontal direction, right? Because you have these tensions here. And even if they're the same, if the angle is different, what happens? Well, if the slope is different, what you're going to have is a net force in the x direction. And if you consider just a small little mass, you're going to have a really large acceleration. And that is simply not possible. Okay? So you really require that the slope of the total string be continuous. All right, so what you have to do now is you have to differentiate this with respect to x and evaluate it at x equals to 0 on each side of the string. So let's first do if you differentiate this with respect to x, what you end up getting is a k1 in the front, and the cosine switches to a sine function. So this is what it looks like. So if I do the derivative of y1 with respect to x, it looks like this. It's minus a. The minus comes because I differentiate a cos. There's a k1 that comes in the front, and now it becomes sine of k1x minus omega t. The second term, if I differentiate that with respect to x, you get minus b, k1, again, sine of k1x plus omega t. All right, now you take the derivative on the other side. Okay, the derivative on the other side becomes minus c k2 sine of k2x minus omega t. Now, again, our boundary condition says we have to evaluate this at x equals to 0. So let's go ahead and do that. All you have to do is substitute x equals to 0 in this expression. So what you get here is minus a k1. This first term goes away. You're left with sine of minus omega t minus b k1 sine of omega t minus c k2 sine of minus omega t. All right, I think I did that correctly. Now we have to use some properties of the sine function. The sine is an odd function. So if you want to switch these to positive values, you have to bring the negative sign in the front. Okay, so the way that this looks like, then this term will become positive. It's ak1 sine of omega t minus bk1. I'll leave this one just as sine of omega t. And then again, if I want to switch the sign here inside the sine function, you have to bring the negative sign in the front. So this becomes C K2 sine of minus omega t. Now this simplifies greatly because you have the same, this should be positive omega t, everywhere. So all you have to do now is simply get rid of those. You can divide through by sine of omega t. And now the second boundary condition looks like this. It's A multiplied by that wave number minus B times the same wave number equals to C multiplied by K2. All right, this is the second boundary condition that we need in order to relate these amplitudes over here. So let's go on the next page and find answers for the ratio of these amplitudes. All right, so here are our two boundary conditions. The goal now is to get two ratios. My goal is to get C over A. That's the ratio of the transmitted to the incident, and also to get the reflected over the incident amplitude. Okay, that's the goal. So one thing we could do to kind of simplify some of the algebra here is we can bring K1 on the other side for equation 2. So if I do that, just kind of divide through by K1. Okay. One thing to remember here is that the speed, again, is omega divided by the wave number. And the speed in medium 2 is omega divided by K2. So if you have this ratio here of K2 over K1, imagine you did this, K2 over K1. Well, K2 would be omega over V2. K1 would be equal to omega over V1. So if you do K2 over K1, guess what? You get omega over V2, and here you get omega over V1. So that simplifies nicely. So the ratio is here V1 over V2. So you can also write this as C V1 over V2 if you write it in terms of the velocity. Let me just get rid of this, clean this up a little bit. Okay, so it doesn't matter which one you choose. I'm going to choose to just write it in terms of the velocity. So let's just use this expression here. Okay. So what do we have to do first? The nice thing about having this equation like this, you see if I add both of these up, the b's are going to cancel. I have plus b over here and I have minus b over here. So if I add up 1 plus equation 2, the way I have it now, it's going to be equal to 2a on the left-hand side. And on the right-hand side, if I factor out a c, I'm going to get 1 plus v1 over v2 multiplied by c. All right, what I want to do now is just put this on a common denominator. So if I bring a v2 over here, I'm going to get v2 plus v1 over v2 multiplied by c. All right, like I said before, the goal was to get the ratio c over a. That's the transmitted to the incident amplitudes. You simply bring v2 on the other side, you get 2 times v2 over the sum of the velocities, v1 plus v2. All right, this is our first equation, written in terms of the velocities. And again, the velocities you can always write in terms of the tension and the line density. Okay, so you could take this a step further. All right, the next thing we need to do now is find what is the ratio of b over a. Well, b over a, you can use any of the equations. Well, what if I use the first one? All right, if I use the first one here, let's go ahead and do that. So I'm looking for let's divide equation 1 divided by a. So what do we get? You're going to get 1 plus b over a, okay, equals c over a. Well, that's nice. That's a good form. This is what I'm looking for right here. I just solved for c over a, which I have over on this side. Only thing you have to do is bring the 1 on the other side, and you're going to be left with b over a is simply c over a minus 1. Okay, well now let's substitute our values. What did we have for the ratio of c over a? I had 2v2 over v1 plus v2, and now minus, oh careful, minus 1. All right, at the end, if you kind of put this on a common denominator, this is what you're going to end up getting. You're going to get that the ratio of b over a, I'm sorry, I'm running out of space here, b over a should be equal to the difference of velocities. Now careful, it's going to be v2 that goes first, minus v1 divided by the sum, v1 plus v2. These are our two expressions relating the ratio of these amplitudes. the reflected and the transmitted amplitude to the incident amplitude, written only in terms of the speeds of the waves in those medium. All right, so these are the two ratios that we solve for. B over A, again, B is the reflected to the incident amplitude. This is given in terms of the difference over the sum of the speeds, and this is called the reflection coefficient of the wave. The other one, C over A, that's the transmitted amplitude over the incident amplitude. Again, written in terms of the speeds. This is called the transmission coefficient of that wave. Now remember our first boundary condition, this was the continuity of the string. You can see again, if you divide through by A, all of these terms, I'm going to call this R, that reflection coefficient. I'm going to call this T, the transmission coefficient. You can see by looking at that first boundary condition, what you obtain here is 1 plus the reflection coefficient is equal to the transmission coefficient. Okay, that's kind of an important relationship for waves. Now recall also that the speeds, right, the speed in any of these media, for example, V1 is simply going to be T divided by mu1. And also V2 is going to be equal to T divided by mu2. All right, so if you do a little bit more work, what you can do is you can write this reflection coefficient here in terms of mu1 minus mu2 over mu1 plus mu2. And this other one you can write it as 2 mu1 over, again, the same thing, mu1 plus mu2. Use the fact that the tension is the same in both strings. You have to do a little bit of algebra here in order to simplify this, but it's not too difficult to show this. All right, now what I want to do is let's look at some limiting cases to make sure these results kind of follow our intuition, because the equations look rather complicated. But if we look at some limiting cases, we can see if it makes sense or not. All right, let's look at some limiting cases here. The first case I want to look at is, what if you simply have one string and it's terminated by a brick wall? Well, if you have one string, you're going to have a mass density. If it's a brick wall, guess what? Mu2 is basically very, very big. Okay, you're not going to move that wall, right? That's what our intuition tells us. So let's look at our reflected and transmitted coefficients in this limit. So mu1 is just the way it is. It's mu1 minus mu2. Mu2 is infinite, all right? So it's much, much bigger than mu1. So what you do is you just simply forget mu1 is very, very small compared to mu2, right? Mu2 is big. It's the dominant term. Likewise, in the denominator, what we do here is forget about mu1 because I'm adding it to something very, very big, right? So what you end up getting here is two big numbers, but there's a negative sign in the front. So this here tends toward -1. Well, what does this mean here? This means that the reflected wave is inverted. So this is what it would look like in kind of a diagram here. What you would have is an incident wave strikes the wall, and the reflected wave now is inverted. The amplitude is exactly what the incident was. It's just out of phase by 180 degrees. Right? B is minus A. Look at the transmission coefficient, right? The transmission coefficient is T. In that case, if mu1 is small, what you end up getting here is, forget about that. We have 2. Mu1 is small. We forget about it. So you're left with 2 over something that's very, very big. 2 divided by infinity is basically 0. Okay? So there's nothing that gets transmitted if it's a brick wall. Everything just gets inverted. Let me just write this. Nothing is transmitted. All right, so that's one of the limiting cases you can do now. All right, let's look at a few other cases. All right, here's our limiting case number 2 I want to look at. We have a light string for the blue one and a heavier string for the green one. The green one has a linear mass density that's 4 times the blue one. So let's calculate our reflection and our transmission coefficients for this case. So all you have to do is substitute the values here. You'll get root of mu1 minus root of 4 times mu1 and divided now by root of mu1 plus root of 4 times mu1. All right, you simplify that, you could take a 2 out of the square root term, so you're left with minus 1 times root of mu1 over 3 times root of mu1. That gives me minus 1/3 for that reflection coefficient. The transmission coefficient now simply looks like this. The denominator ends up being the same thing, right? So it's actually 3 times root of mu1. So this here gives me 2/3. So this is what the wave would look like, right? If I have an incident wave, let's just terminate it right here at the boundary. That's the amplitude right here of this incident wave. It tells me that the reflected first is negative. So that tells me that it's inverted, but the amplitude is 1/3 of this one. So it should be pretty small compared to that other one. Again, the red one is traveling to the left. The right one here is traveling to the right. Okay, that's the incident. Reflected. And here I'm just taking a snapshot in time. Now what about the transmitted? Our transmitted ratio, if you look at it, it's a positive value. It's 2/3. So if you have an amplitude over here, the amplitude of the transmitted wave should be smaller, but it's not inverted, right? And it still travels in this direction. This is our transmitted wave, propagating at speed v2. Okay, that's kind of the relationship here between the amplitudes given this reflection and transmission coefficient. All right, let's look at one more limiting case. All right, the last case I want to look at here is the uniform string. So again, now the strings are the exact same thickness, for example. So we have the line density of medium 1 is the same as line density of medium 2. So it's basically just one uniform string. So what would you have in that case? Well, our reflection coefficient and our transmission coefficient. Well, you just make the values the same. Look what happens here. If I take the difference between two things that are the same, I'm going to get 0. What about the transmission? So I'm going to get basically 1. So what does this mean? If the reflection coefficient is equal to 0, it tells me that there is nothing that is reflected. And there's no reason for anything to be reflected. It's basically just one string. So you simply have a wave that simply propagates to the right and just keeps on going as though nothing was there. Propagates at speed v1. Guess what? The transmission then is 1, right? So it's exactly the same. Okay? The boundary is no different than any other point on the string. Right? The wave passes simply right through it, okay, in this limiting case. All right, the last case I want to look at is kind of a tricky one. At case 4, it's what happens if the string on the right-hand side is not there, or it's really, really light, right? We're going to take the limit when that mass density goes to 0 for that second medium, for the green string. What happens in that case? So we have our reflection coefficient in this case, which is mu1 minus 0 over mu1 plus 0. Well, this here gives me 1. Okay, so that kind of is okay. That simply means it's a complete reflection, right? There is no inversion in this case, right? It's simply perfectly reflected wave. What about the transmission coefficient? Now, if you start substituting the values in here, what you're going to get here is you're going to get a value of 2. Now, you may be wondering, well, that just doesn't make sense. Now, this is kind of a little bit of a technicality because, remember, if mu2 goes to 0, what does it mean in terms of the speed? Remember, the speed of that wave is the tension divided by v2. So it basically means that the speed is going really, really fast, number one, and that the wavelength is basically infinite for that wave. That means that the whole string basically moves up and down with an infinite wavelength. One thing to note about if you're going to calculate the energy, all of the energy ends up being in the reflected wave. There can't be any energy in the transmitted wave because the string has no mass, right? There's no mass on this side. So it actually carries no energy. So it's kind of mathematically, it looks like a funny case to have a transmission coefficient larger than 1, but you do have to consider these other aspects of the string. So there would be no energy for whatever is on this side, so it doesn't really matter. Okay? Hi, so everything I did in this video, I assumed that the tension was the same. T1 was equal to T2. We made that argument, and that would be true if the strings are connected to each other. Now there is a more complicated case. If the string, the blue one was connected to this ring, right, and the ring was attached to a pole where there's no friction between the ring and the pole. And then on the other side, I connect that green string. Now in this case, you don't necessarily have to have the same tension force in both of those strings because it's going to be balanced out by the force of the pole acting on the ring. Okay, so it's a little bit harder case to deal with in this case, but the tension in that one does not have to be the same. You're going to get to similar expressions. It also introduces the concept of impedance if you do it this way. I'm going to leave that for a different video. It's a bit more of an advanced topic. All right. Thanks for watching, folks. I appreciate your support. Remember to subscribe to the channel, like the video if it gave you some help. All right. See you next time.